Hello everyone. So in today's video, I'm going to go over the Tensor API present in TensorFlow. I'm going to go over the documentation as well as run some code samples on this collab notebook. Alright. So a tensor is a multidimensional array of elements. A tensor is how you send in elements into. So you can send it through other data types as well, like other aggregation things such as numpy arrays as well. But a tensor is something which is most commonly used to send in data into models or into processing pipelines. So some key points: all elements are of a single known data type. So you can't have like strings and integers together. All of them will have the same data type. And when writing a TensorFlow program, the main object that is manipulated and passed around is the tf.Tensor. So the tensors are usually used, and it has two properties: a data type, which indicates what the data in it, what type the data in it has, and a shape. So since it is a multidimensional array, it also has a shape. Right. So there's this thing mentioned about eager execution and graph execution. So the difference in them is, suppose you have a set of operations. In the eager execution mode, they will immediately be evaluated, but in the graph execution mode, it will first create a computational graph and later the evaluation part takes place. So if you're just a beginner, you don't really need to know a lot about this, but it's good to know that these two modes exist. So by default, the eager execution mode takes place, so the results are calculated immediately. So if we run this code sample, you can see, sorry, I'll just let it run for a bit, but the output is this. So you can see the multiplication. tf.matmul is basically matrix multiplication between these two tensors. tf.constant creates a tensor with these values, and matmul just does a matrix multiplication. And when you print the tensor, you can see these are the values. So after the matrix multiplication, this new matrix is created. The shape is again 2 comma 2, and the data type is float 32. So you can see the original tensor also had a float data type. Alright, I also need to import TensorFlow. So TF is just a alias for TensorFlow. Right, so while that runs, let's continue. So note that during eager execution, you may discover your tensors are actually of the type eager tensor, and this is an internal detail, but it does give you access to a useful function, that is numpy. So what does this mean? So let's just get the type of it. You can see it says it's an eager tensor. So what the eager tensors can do is, if you do a .numpy call on an eager tensor, you can extract the value out of it. So this is now, let's just convert this into say x, and then if you check the type of x, it's a numpy array. So you can get the value out of it, and it is no longer a tensor. You can now use numpy functions on this x array. Alright. So in TensorFlow, TF functions are a common way to define graph execution. So TF functions are basically TensorFlow functions. Uh, Probably in a later video, I'll also be covering these, so you can, if you're in a hurry, you can have a look at the documentation. Also, tensor shape, that is the rank of the tensor and the size of each dimension, may not always be fully known. So in tf.function definitions, the shape may only be partially known. So this is something which you can do. For instance, if you don't know how many data items are going to be there in your tensor, so how much input the user is going to give, you can not give that information, right? And at a later stage, that information can be inferred. So that is why graph execution helps. Most operations that produce tensors give us tensors whose shapes we know, but in some cases we don't really know the shape. So that is only like for the program to know that shape, the program has to be at execution time. While writing the code, you won't be able to tell the program what the exact shape is. So that is also possible, and a TensorFlow also handles that. There are some specialized tensors as well. So you can create a variable, a constant, a placeholder, a sparse tensor, or a ragged tensor. So all of these I'll be covering in future videos. So let's have a look at this example as well. So what do you expect? You have a numpy array. So for that I need to import numpy as well. You then create a constant tensor out of that numpy array, and then you say that I want the zeroth index element to be a 4 now. And once you run this, you can see that the value at 0 is now a 4. So this is just a basic example, right? So if you have a look at this function, this definition for the API, you can see that it takes in three things: the op, the value index, and the d type. So the op is basically the operation that computes this tensor. The value index is an integer. So this is the index of the operations endpoint that produces this tensor. So at different stages of the operation, different tensors can be produced. And the d type is basically the data type of the element stored in this tensor. Also, it raises a type error if the operation which you're passing is not an operation. Also, like uh, other things, for instance, numpy arrays have a lot of attributes. Tensors also have a lot of attributes. So you have a device. So if I just take the example of B, so B is a tensor. If I check b.device, I find that it is currently on my CPU. So to move it to my GPU, there are special commands which can be run. You can also access the data type. So b.dtype. So it's an int64. You can look for the graph which contains this tensor. So I'm not sure if we will have a graph even, because we're not doing anything special. Yep. So since we are in the eager execution mode, uh, you do not have a graph attribute available to check look at. You can also give names to your tensors. So since I have not given a name to the tensor, there is also in eager execution mode, the name is a meaningless attribute. You can also have a look at the op, but again, we are in eager execution, so this is also meaningless. The shape is something which you can always have a look at. So if you take a look at this example, you have 5 entries, so the shape is 5. Also, an important thing to note, tf.Tensor.shape is also equivalent to tf.Tensor.getShape. So if you have a look at this here, b.shape and b.getShape, you get the same outputs. Also in a tf.function, or when you are building a model using the keras tf.keras.input layer, so you tell the model the input dimensions through this. They return the build time shape of the tensor, which may be partially unknown. So you might know that it will have two values per index, but you might know how many indexes it has. Also, a tf.Tensor shape is not a tensor. It you uh, right. So basically, this is not a tensor. That's all it's trying to say. And I'm not sure how do I remove. Yeah. So if we have a look at this here, what's the type of the get shape that we have? So you might think that this is a tensor, but this is a tensor shape at object. This is not a tensor. you can have a tensor as well returned. So if you do a tf.shape of b, so tf.shape is a function, you can see that it returns a tensor, and the tensor is the shape. So the value is the shape. The value index is just the index of this operation in of the tensor in the operations, but again, since we are in the eager execution mode, uh, oh sorry, it should be b dot value index. This is a meaningless thing, right? So there is this function called method called consumers. So if you are in the graph mode, you can have a look at which all operations are using this tensor. So if you do a b dot consumers call, but this is again meaningless since we are in the eager execution mode. Probably in the future video I'll cover graph execution mode and show this stuff. You have the eval mode, which evaluates the tensor in a session. So what this will basically do is it will look into the computational graph, do all the operations which would be required to compute this tensor, and then return the output. Uh, then you have experimental ref. This is a deprecated function, and there is no like doc string for it as well. Get shape returns the shape of the tensor. So this is a tensor shape object which returns the shape. So in eager execution, the shape will always be fully known, but in graph execution, that is not the case. So again, these two functions are equivalent, which is stored in the docstring above. When executing in a tf function or building a model using tf.care as input, tensor.shape may return a partial shape. So for the dimensions where the shape is not known, you'll get a none. So if we have a look at this itself, you can see you've just given a shape 10. So you know that the input, each individual input will have a shape of 10. So it will have 10 values, but you don't know how many inputs there will be, right? So that is why there is a none for the unknown dimensions. The shape is computed using shape inference functions that are registered for each TF operation. So for different TF operations, you have these shape inference functions. Also, the return tf.tensor shape is determined at build time without executing the underlying kernel. It is not a tensor. If so, we've already seen this quite a few times. If you need a shape tensor, then either convert the tf.tensor shape to a tf.constant, or you can just use tf.shape of tensor function, which returns the shape at execution time. And this is useful for debugging and providing early errors because you can write unit tests for the same. So let's have a look at this example. So when you're tracing a tf function and no ops are being executed, the shapes are unknown. So you have this matrix multiplication function, you do the matrix multiplication and then you print the shape of results. The shape inference functions propagates these shapes to as much extent as possible. So if you have the none comma 3 shape and a 3 comma 5 shape, then you get a none comma 5 shape. So it tries to retain as much shape that is it possibly can, so it does not totally rule out this 5 as well. And tracing may fail if a mismatch is detected, so you cannot multiply a matrix which is say m cross 3 with a 4 cross 5 matrix, because you cannot you need to have the same dimensions for the last dimension of the first and the first dimension for the second tensor. So that when it shows that there is a mismatch error, the none is represented by a question mark. In some cases, the inferred shape may have an unknown dimension if the caller has additional information about the value of these shapes. So what you can do is you can use tf.ensure shape or tf.set shape. So I guess ensure shape is now the more recommended function, and that can be used to augment the shape. So suppose you have this uh, tensor A, then you can ensure that its shape is now 5 comma 5, and then you present the shape. So you know that initially you have no information about the shape, so it's a none comma none object, but you know that after execution the user wants it to be a 5 comma 5, so it will be the result will have a 5 comma 5 shape. Again, if the user gives something which cannot be converted, then it would throw an error. Alright, so ref basically returns a hashable reference object to this tensor. So in Python you have the notion of sets and dictionaries. You cannot directly put tensors into sets and dictionaries, so you need to use this ref function. Earlier, prior to TensorFlow 2.0, you had this dot hash function, but it is no longer present. So if you try to execute this, you have three tensors and you try to create a set, you get this error that tensor is unhashable. So you need to use tensor.ref as the key. Uh, how do I remove this? It's pretty annoying. Yeah. So when you pass it through, if you do this instead, it would now big work. You can see the tensor set has been created, and if you have a look at the tensor set, you can see that it is not something which you can uh, it is something which you can directly see. So you have these values right here. You also have this reference wrapping thing written, which I believe is due to this ref call. uh, you can also create a dictionary in the same sense. So you can say that for the extensor, the key is extensor and the value is 5 and so on. So then you can also access these values. So if you do x.ref on the tensor dictionary, then you can get the value corresponding to it. You also have deref that returns the original tensor. So you have, suppose you create something a, say you create a hashed tensor which is just x.ref. It's not a hash tensor, let me just call it a ref tensor, ref extensor. And if I print ref extensor, I get this. I can get back x by just doing ref extensor dot deref. And if I now have a look at x, it's the original tensor. So I guess this part makes sense now. You also have the set shape function. Yeah, what I was talking about is also mentioned right here. It is recommended to use in show shape instead of set shape, because in show shape provides better checking for programming errors and can create guarantees for compiler optimization. So if they are doing the same things and one is doing it better, then I guess there is no point in using the old version, right? So but still you should know how you can do this. So you have, suppose you have this tensor t and you want its shape to be now 1 comma 3, you can do the same. And now if you print t, uh, it's currently the same shape, but if you pass in none for some axis, then again it will auto compute what shape should fit there, and it retains the shape. But if you try to convert it to some shape which it cannot be fit into, because you need 5 elements to create a 1 comma 5 shape tensor, then you get this incompatible error. Also, when executing in a tf function or building a model using tf.keras input, tensor.setShape will merge the given shape with the current shape of the tensor and set the tensor shape to the merged value. So if you have these shapes and you do a set shape in the tf function, then it will auto fix this. So basically what happened right here, the shape was 3 none comma none comma none comma 3, and then you wanted it to be none comma 2 to 4 comma 2 to 4 comma none, so it merged the last dimension with 3. because it knew that that is what is there in the initial shape. So the main use case for this is to provide additional shape information that cannot be inferred from the graph alone. So at different stages, if you get to know different information, you can combine them like this. For example, if you know all images in the data set have shape 28, 3, so that this is 28x, 28y and 3 channels, I guess, then you can set it using uh, the image dot set shape function. So the initial shape is unknown, you've decoded it, but you only provided a number of channels information, but later you've provided the information, so the final shape is what was present here. These two got merged essentially. There's also the tf.io.parse tensor function, which could return a tensor with any shape. Even the tf.rank is unknown. So if you know all your serialized tensors will be 2D, you can set the shape. So you can just set them to be non-common none, which makes them 2D tensors. And initially the shape is unknown because you just know that you're getting a tensor input which you're parsing using tf.io.parse tensor. But after the set shape call, it has the non-common none, which is a 2D indicative of a 2D shape. So suppose you had this tf dot ones, so you created a 5, 3 array of ones, then you serialized it, so you can have a look at the data type of the serialized tensor. You can also have a look at the shape of the serialized object, but once you create a parse from the serialized tensor, you get back the shape information. So suppose you have another example where you serialize a 3D tensor, then you can retrieve it and get back the shape. So the function still runs even though it's set shape non-common none. So I guess that is it for this function. Then you have the absolute value. It computes the absolute value of a tensor. So if you have this tensor, it will take the absolute value of every element. If you have operations within the tensor, so if you have complex numbers within the tensor, it will also calculate the absolute value, which is under root of a square plus b square. So it can take in complex tensors as well as integer tensors. For add, you can just invoke it using the add operator, and this is pretty obvious, I guess. You create two tensors, you can add them. Then there are a bunch of functions which are just element wise operations, so you can take the AND of two tensors. You can take there is no docstring for this, so I'm not quite sure what this does. But for the bool function, dummy method to prevent a tensor from being used as a Python bool. So this method raises a type error when the user inadvertently treats a tensor as a boolean. So if you uh, like have conditions where you're using the tensor as a boolean, then this will raise a type error. And so if tf dot constant true, this will raise an error. If you cannot like compare two tensors in this sense, right? If you want to compare, you need to unpack, so you need to use a dot numpy or something of that sort. You can do an element wise division as well, so divide x by y element wise using Python to divisor operator semantics. So this is a deprecated function, and you should use tf.mag.divide. You have an equal function which compares two tensors for element-wise equality if they are broadcast compatible. So what broadcast compatible means, even if their shape is not the same, you can broadcast the shapes and have a look. So if you're not familiar with broadcasting, I'll recommend going through it. I guess the NumPy docs have a lot about broadcasting. This behavior is different from tf.mag.equal, which raises an exception if the two tensors are not broadcast compatible. So this returns a false, that raises an exception. So this method is exposed in TensorFlow's API, so library developers can register dispatching for Tensor.E to handle it, allow it to handle custom composite tensors and other custom objects. You have flow division. You also have greater than equal to, which is GE. So let's have a look at these examples. So you can see, um, okay, so this is what the output is. This is not like part of the function itself. So you can see at each element it tells where all it fits in. For the second one, again it will now broadcast. So 5 is greater, 4 is not greater than 5, so false. 6 is greater than 5, so true, and 7 is greater than 5, so true. You have get item. So this is an overload for the tensor.getItem function. This operation extracts the specified region from a tensor. So you can uh, do this similar to how you do indexing in NumPy. And so let's have a look at some examples. So suppose you have a tensor, you can extract the elements from the second index to the minus 2 index, which is essentially the second last element. So since you're starting from the second index, which is 3, and you're going to the minus 2 index, which is not included, so you'll get 3 comma 4. So suppose you want to skip every other row and reverse the order of the columns. So what you'll do is, uh, this second part, if you're familiar with Python string reversal, you know that this reverses the string. You are taking everything, and your step is a negative 1 step, and here you're taking everything and your step is a step of size 2. So you're just taking the first one and the last one, you're skipping this, and you're also reversing it. Now you're using how to use scalar tensors as indices on both dimensions. So you can take tensors as indexes here. So you can see the 0 is treated as an index, and you'll get 3 because that is present at the 0th row and second column. 0th row, second column. You can insert dimensions at different places. So you can add a new axis at different places, and you can see the shape changes accordingly. So if you add it at the outermost place, you'll get one more extra dimension on the outermost side. If you add it one in, then you'll get it one layer dimension inner to the outermost, and if you add it even at the innermost dimension, then it will be added to the innermost dimensions. You also have ellipses, which are 3 equivalent operations. So okay, so you can do the same thing in 3 different ways. So one way to add an axis would be this, tell it to add it to the outermost place. Another way would be to add it and then use a dot dot dot, which would automatically fill in the rest. And finally, since you only need to add it at the first index, outermost index axis, then you don't need to even specify the rest of the information. You can also create masks in some sense similar to how you do it with Panda data frames. So you create a mask of values greater than 2, and then you pass 4 through it. You will only get the values which are greater than 2. So this API is again to handle custom composite tensors and other custom objects. You have GT, which is greater. You have invert, it LE is, I guess, less than equal to. Then you have length, you have less than, which does not include equal to. You have matmul, which is matrix multiplication. You have mod, which is modulo, which you have mul, which is uh, column wise multiplication. You have any, which is not equal, I guess. Then you have neg, which does a negative element wise. You have non-zero, which I guess generates a boolean. You have or, which does uh, boolean or. You have power, which does power, so it does exponentiation. You have rad, which does addition. So I'm not sure why you have a separate RAD, right? So let's have a look at the documentation. This method is exposed in TensorFlow API so that developers can register dispatching for add to handle custom operations. So okay, so once you call the TensorFlow.add, this is invoked. You have all these functions which are invoked when you call them, I guess. Um, right, so these are the same names with the R, so I guess these are what are invoked internally. And right, so you have functions like XOR, TrueDiv, which does integer division, I guess. You have, and basically for anything else, I'll recommend just exploring the documentation, so because it has everything mentioned here. So you can see the order is a bit haywire because TrueDiv here occurs here while our TrueDiv occurs above it, contrary to how the order was being followed so far. But I guess you can still do a quick search and you'll get these functions. So I guess that is all for this video. About this notebook, if you wanted, I've created this repository. I'll be adding it here and you can have a look at it there as well. So I'll have all of these linked in the description. Thank you guys for tuning in. Hope to see you again next time as well.